Hello, this video includes information on equilibrium problems and ice charts.
So we're looking at a reversible reaction. The reaction is at equilibrium. We're given equilibrium values for the nitrogen, the hydrogen, and the ammonia. And we want to calculate K, and we're going to calculate it in terms of concentrations. That C often is just assumed and you don't see it. You would have to put P if you're talking about in terms of pressures. For this particular question, we want concentrations of nitrogen, hydrogen, and ammonia. We're given moles in a 5-liter container. So we have to calculate the molarity first before we can do anything else. So to calculate molarity, I'm going to do it for nitrogen and then have you do the hydrogen and the ammonia. So to calculate the concentration or the molarity, we take the moles and divide it by the volume. So 1.50 moles divided by 5.00 liters tells us that the molarity of the nitrogen gas in this equilibrium mixture is 0.300 molar. 3 significant digits here, 3 significant digits here. We're rounding to 3 significant digits here. So we have to put those zeros in there. So go ahead on your own, calculate what the concentration of the hydrogen is, and calculate what the concentration of the ammonia is. All right, so for hydrogen, 4.45 divided by 5.00. Make sure you have 3 significant digits. So 0.890 would be hydrogen. Okay, so 7.05 divided by 5. So yeah, 1.41 moles per liter, or 1.41 for the molarity. We want to calculate K. So the next step is we have to write a K expression. Make sure that you do that for every step. Actually, I don't want to do it for you. Okay, write your K expression. Let's do that as a review. So remember that K is products over reactants raised to the power of the coefficient in the balanced equation. Super important that we always write a K expression when we're looking at an equilibrium question. Remember also that we only include ions and gases. Liquids and solids don't get included in there, but they're all gases. This is a homogeneous equilibrium for this one. To write our K expression, we've got our product, so ammonia squared, over our reactants, so hydrogen to the first power times nitrogen, sorry, to the first power, times hydrogen to the third power. So now that we've written the K expression, we know the equilibrium concentrations. We're going to plug these numbers into our expression and get our value for K. And there are no units for an equilibrium constant, so you don't have to worry about that part. So plug them, actually write the numbers down, then plug them into your equation. Okay, so 1.41 squared divided by 0.300 divided by 0.890 cubed. Order of operations is important in your calculators. Okay, plug the numbers in and see what you get for your value of K. Okay, so I'm plugging in the numbers, and this is what I would expect, to get full credit. You want to show all of your work. It's a process. And in your calculator, you would put 1.41 squared, I would say equals, divided by 0.300 equals, divided by 0.890 cubed. That's really the best way to put that into your calculators. And if you put them in the calculator with the right order of operation, you should get 9.40 for your answer. 3 significant digits here. Let's put 3 significant digits in our K value. So now we're going to look at how K will change if we change the balanced equation. So we have this equation. Okay, we've got nitrogen reacting with hydrogen to produce ammonia. We know that K equals our products over our reactants raised to the power of the coefficient in the balanced equation. But let's say that we were to take this reaction and multiply it by 2. Okay, so this is a 1:3:2 ratio. So now we've got a 2:6:4 ratio. We've multiplied all the coefficients by 2. Well, when we write the K expression, it still would be the products over the reactants raised to the power of the coefficient in the balanced equation. But because we doubled the coefficients, this now becomes a 4, this becomes a 2, and this becomes a 6. Now, how can we kind of shorthand that up? If we have an equation and we know the K value, and we take that equation and we multiply it by a coefficient. So in this case, we're multiplying it by 2. We can take K and square it, and that'll give us the K value for that new reaction. So whatever we do to the coefficients in the balanced equation is what we would put here. And that's how we can figure out what the new K value would be. So if the stoichiometric coefficient in the balanced equation are multiplied by a factor, the new equation is equal to the original equilibrium raised to the power of the factor that we multiplied our equation by. So let's look at something else. Let's say that we have nitrogen and oxygen producing nitrogen monoxide. Okay, well, the concentration of the products over the concentration of the reactants raised to the power of the coefficient in the balanced equation. And then let's say that we have a second equation. So we've got NO plus O2 gives us NO2. We can write a K expression for that second reaction. Again, products over reactants raised to the power of the coefficient in the balanced equation. Now, we've talked about Hess's law, where we can add these two reactions together and it gives us the overall reaction. Okay, well, the 2NO is here and here, that cancels out. And we get N2 plus 2O2 yields 2NO2. Well, to calculate, if we know what K1 is and we know what K2 is, we can calculate what K is for this overall reaction. So if 2 or more equations can be added to give an overall reaction, the equilibrium constant for the overall reaction equals the product of the equilibrium expressions for the two reactions we're adding together. So in other words, K for this overall reaction would equal K1 times K2. Well, we calculated or we figured out what K1 is here. We figured out what K2 is here. If we were to multiply these two equilibrium expressions together, NO squared here and here cancels out, and we're left with our products over our reactants raised to the power of the coefficient in the balanced equation for the overall reaction. So if 2 or more equations are added to give an overall equation, the product of the K values for the individual equations will equal the overall equation. Just manipulating what K is. All right, so now we're going to look at some more problems. So here, okay, it tells us that we take 0.200 moles of nitrogen gas and 0.600 moles of hydrogen gas in a 1 liter container. And the pressure is 10.0 atms. what is the value of the equilibrium constant? That means we want to calculate K if the equilibrium mixture contains 0.00320 moles of ammonia. Well, this 0.200 and this 0.600 are not at equilibrium. They're before the reaction takes place and before equilibrium is established. So what we're going to do is we're going to make what's called an ICE chart. And that's going to help us to kind of organize our numbers. So in our ICE chart, I stands for initial. So in this case, the initial concentration of nitrogen was 0.200 moles in a 1 liter container. So 0.200. Hydrogen is 0.600 moles in a 1 liter container, but there wasn't any ammonia initially because the reaction hasn't started. And this is our I in our ICE chart. Now, the C is for the change that takes place in order for us to establish equilibrium. And the change is a stoichiometric change. It's based on the balanced equation. So in this case, X amounts of nitrogen is going to be reacted. That's why there's a negative sign. 3X of hydrogen is going to be reacted. That's why we have the negative sign, and it's a 1-to-3 ratio. 2X of ammonia is going to be produced. And we have a plus sign here because we're making the ammonia to get to equilibrium. So the E part of this ICE chart is equilibrium. So we've got initial, change, equilibrium. ICE charts are a way for us to organize our information. So at equilibrium, we're going to have 0.200 minus X for our nitrogen. And we have 0.600 minus 3X for our hydrogen. And we're going to have 2X for our ammonia. And it tells us that that's 0.00320 moles per liter. So it's giving us what 2X equals. Okay. An ICE chart is a way for us to organize our information. Now, what can we do with that? Well, if 2X equals 0.00320, that means X equals 0.00160. And if we know X, we can figure out the equilibrium concentration of nitrogen, 0.200 minus X, and the equilibrium concentration of hydrogen, 0.600 minus 3X. And once we calculate the equilibrium values for everything, we can write a K expression and calculate K, or our equilibrium constant. So at equilibrium, nitrogen will be 0.200, that's how much we started with, minus 0.00160, which is how much had to react to make our ammonia. So at equilibrium, we have 0.1984 moles per liter of nitrogen. We're going to carry an extra significant digit along. For our hydrogen, we would take 0.600 and minus 3 times X, where X is 0.00160. So at equilibrium, hydrogen is 0.5952 molar. So now we know the equilibrium concentration of nitrogen. We know the equilibrium concentration of hydrogen. We were given the equilibrium concentration of ammonia. We can calculate K. Now, the first thing we have to do is write an equilibrium expression You're going to get a point off if you don't write that when you do your problems. So products over reactants raised to the power of the coefficient in the balanced equation. And then once you write your K expression, plug in the equilibrium concentrations and calculate K. Okay, make sure you write your K expression. So products over reactants raised to the power of the coefficient in the balanced equation. And then we know the equilibrium values. We're just going to plug those numbers into our K expression, okay, into our equilibrium expression, and figure out what K is. And again, you know, the order of operation, how you're plugging it in the calculator is super important. Okay, so make sure you practice doing that so that you don't run into a problem with you can show all your work on paper and you get the wrong answer because you're not plugging it in right. So 0.00320 squared equals divided by 0.1984 and then divided by 0.5952 cubed equals 2.45 times 10 to the minus 4. Good. Now, this is a small number. That means that equilibrium is established before we produce very much product. So the reactants are favored when the system reaches equilibrium. So whereas the problems you were looking at before, you were just given the equilibrium values and you calculated K, this time you had to figure out what the equilibrium values were. So let's look at another one, same kind of problem. So we have a reaction and it says that we put 0.380 moles of HI in a 1 liter container. That means the moles equals the molarity because we're dividing by 1. It doesn't mention anything about them adding hydrogen or iodine to the container originally. That means their initial values are 0. And then it says the reaction when it gets to equilibrium has an iodine concentration of 3.80 times 10 to the minus 2. We want to calculate K. We're going to start with an ice chart. We always start with an ice chart. Okay. I stands for initial. C stands for the stoichiometric change. E stands for equilibrium. So originally, we have 0.380 moles per liter of HI, and we don't have any hydrogen and we don't have any iodine. Based on the stoichiometry in the balanced equation, 2x of HI is going to react. The negative sign is because it's reacting. X amount of hydrogen and X amount of iodine are going to be produced. So at equilibrium, we're going to have 0.380 minus 2x, X, and X. Now, the question tells us that at equilibrium, iodine is 3.80 times 10 to the minus 2. So it's giving us X. So if we know X here, it's the same as here. And we can figure out the equilibrium concentration of the hydrogen iodide by taking 0.380 and subtracting 2 times X. Once we calculate the equilibrium values, we'd write a K expression, plug in the equilibrium values, and calculate what K is. So let's see how you do with that. So it tells us that hydrogen or that iodine is 3.80 times 10 to the minus 2. Since it's a 1-to-1 ratio, oops, sorry, I did the other way. The hydrogen iodide is going to be 0.380 minus 2x. This 2x came from the stoichiometry in the balanced equation. So 0.380 minus 2 times 3.80 times 10 to the minus 2. That means at equilibrium, HI is 0.304. And hydrogen is the same as iodine. So now that we have the equilibrium values, write a K expression, plug in the numbers, watch your order of operation, and solve for K. Okay, so your K expression is hydrogen times iodine divided by hydrogen iodide squared. We plug in our values. So 3.80 times 10 to the minus 2 times 3.80 times 10 to the minus 2 divided by 0.304 squared. And that gives us a K value of 1.56 times 10 to the minus 2. Again, a small K value, which means our reactants are favored, and we didn't produce much product before equilibrium was established. All right, so let's look at another question. And these are all, once we kind of get a feel for how these equilibrium problems go, they're all very similar types of problems. So for this one, we're given a reaction, okay? It's a reversible reaction, it's at equilibrium. So it says, suppose you start with 0.0200 moles of carbon monoxide and water in a 1 liter container. Calculate the molarity of each substance at equilibrium. And it gives us K. So this time, we're not calculating K. Really, the questions are either we're given the concentrations or we can figure them out, and we want to calculate K, or we're given K and we want to calculate concentrations. But we're going to always do the problems in a very similar way. So we're going to write an ice chart. Okay, again, ice, I stands for initial, C stands for change, E stands for equilibrium. Okay, so it tells us we've got 0.0200 moles per liter, 0.0200 moles per liter, and no carbon dioxide and no hydrogen to begin with. Now, in the previous problems, it gave us one of the equilibrium values so we could figure out all the other ones. It doesn't do it here. But we can figure out the change. It's the stoichiometry. We know that some of our reactants are going to react. We don't know how much, but we know they're going to be the same because it's a 1-to-1 ratio. We know we're going to be producing product. We don't know how much, but we know based on the stoichiometry, it's going to be the same amount. So that means at equilibrium, we're going to have 0.0200 minus X, 0.0200 minus X, X, and X. All right. So we write our K expression. Ice charts and K expressions are like the key to equilibrium problems. This time we know K, so we'll plug in 0.580 for K. We don't know what carbon monoxide and hydrogen are, but we know that they're both going to be equal to each other, so we're just going to say they're X times X. We don't know carbon monoxide or water, but we know they are both the same, and they're 0.0200 minus X. So really, we could simplify this and say X squared over 0.0200 minus X. Now, both the numerator and the denominator are squared on the right-hand side here. And our goal is to solve for X so we can figure out the equilibrium concentrations for everything in the reaction. So if we want to solve for X, the first thing we're going to do is we're going to get rid of the squares. And to do that, we take the square root of both sides. So the square root of 0.580 is 0.760. The square root of x squared is x. And the square root of 0.0200 minus x squared is 0.0200 minus x. So now we have a little bit of algebra to do. We want to solve for x. So we're going to take 0.0200 minus x and get it out of the denominator. We're going to multiply both sides by 0.0200 minus x. That gives us x equals 0.0760 times 0.0200 minus x. Well, the next thing we're going to want to do is get rid of the parentheses. So we're going to distribute that 0.076 or 0.760. And we get x equals 0.0152 minus 0.760x. Now we've got x on the left-hand side of the equation, and we have x on the right-hand side of the equation. So now we want to get x on the same side. We're going to add 0.760x to both sides of the equation. And then to solve for x, we're going to divide both sides by 1.760, and that would give us x. Now, we haven't answered the question yet. We've solved for x, and in math, you solve for x and you've kind of answered the question. But what this wants to know is what are the equilibrium concentrations? So we want to actually identify them. So to calculate the equilibrium concentrations, well, the carbon dioxide is X and the hydrogen is X. And the carbon monoxide and the water are both 0.0200 minus X. So carbon monoxide is 0.0200 minus X. Hydrogen is actually the same thing. Carbon dioxide is X. And hydrogen is also X. So in this kind of question, we were given the initial values, we were given K, and we wanted to calculate the equilibrium concentrations. And again, the key to any equilibrium problem, write an ice chart. It helps you to organize the data. Write a K expression, and really the problems go one of two ways. Either you know the concentrations and you're calculating K, or you know K and you're calculating concentrations. So let's look at another one. It gives us the equilibrium constant. Okay, so K equals 10.5. We've got our reaction at equilibrium. It says calculate the equilibrium concentrations of reactants and products when 0.252 moles of reactant, CH2Cl2, is introduced into a container. Well, it doesn't mention the CH4 and it doesn't mention the CCl4. There's 0 initially. If it doesn't mention it, it's not in the container to begin with. So we're going to start with our ice chart. Okay, we start with 0.252, 0, and 0. The change is stoichiometric, so negative 2x will react X and X are produced. So at equilibrium, we have 0.252 minus 2x, X, and X. So from there, we want to write a K expression. Okay, write your K expression and then match it up with what I put up there. Products over reactants raised to the power of the coefficient in the balanced equation. The concentration of CH4 times the concentration of CCl4 divided by the concentration of CH2Cl2 squared. Now you want to fill in what you know. So we know K, and we are going to plug in these values for equilibrium. So plug into our equilibrium expression what you know. So we have 10.5. This was given to us. We don't know CH4, but it's X based on the stoichiometry in the balanced equation. We don't know CCl4, carbon tetrachloride, but it's X. And we don't know CH2Cl2, but it's going to be the initial amount minus the amount that reacts. And we have to remember that because we squared it in the expression, we're squaring it here. Now, the math becomes the same as the math we did before. We've got X squared over 0.252 minus 2X squared. Follow what we did in the last question. Take the square root of both sides, isolate X, solve for X, and then once you solve for X, plug them back in here and calculate your equilibrium values. And whenever the numerator and the denominator are squared, this is the way we want to solve the problem. Take the square root of both sides. And remember, just because you solve for X doesn't mean you answered the question. Once you figure out what X is, you need to go back into your ice chart and figure out what the equilibrium values are for your reactants and your products. Okay, so we're going to multiply both sides by 0.252 minus 2X. Then we're going to isolate X, and we should get 0.109 for X. So that means that CH2Cl2 is going to be 0.252 minus 2X, which gives us 3.37 times 10 to the minus 2. And then the methane and the carbon tetrachloride are equal to each other, and they're both equal to X. So and there should be a molar there. There should be a unit. 0.109 molar, it should say. Again, the key, write a nice chart for an equilibrium problem, write a K expression, and then either you're given the concentration and you're trying to find, or you're given concentrations and you're trying to find out K, or you're given K and you're trying to find out concentrations. So the initial concentration of PCl3 and Cl2 are 0.0371. If the initial concentration of PCl5 is 0 and K is 0.021, we want to calculate the concentration of PCl3 at equilibrium. All right, so we'll do this step by step. So the first thing I want you to do is write an ice chart. Okay, initial stoichiometric change and equilibrium. Okay, don't go any further than that yet. Write your ice chart, plug in your numbers. This one's starting with the PCl3 and the Cl2, that doesn't matter. Okay, so we've got 0.0371, 0.0371, and 0. Those are the initial values. The change, well, it's a 1:1:1 ratio, but look at the way the change is set up. We can't have any PCl5 reacting because we don't start out with any of it. But the PCl3 and the Cl2 are going to react. We don't know how much, but we know they're going to react in the same amount because it's a 1:1 ratio. So minus X, and plus X. So at equilibrium, 0 plus X, so we've got X amount of PCl5 at equilibrium, and 0.0371 minus X for both the phosphorus trichloride and the chlorine. All right, so we wrote our ice chart. Now, write a K expression. Products over reactants raised to the power of the coefficient in the balanced equation. Okay, so once you write your K expression, substitute in these equilibrium values out of your ice chart. Okay, so PCl3 times Cl2 over PCl5 equals K. Now, you could write 0.0371 minus X times 0.0371 minus X, but because these values are equal to each other, I'm just going to write them once and write squared. Okay, so 0.0371 minus X squared over X. The K value that we're given is always going to be for the way the reaction is written, not necessarily the way the reaction takes place in the container. Okay, so we know K. So we're going to plug in 0.021 for K. We have 0.0371 minus X squared over X. All right, well, we've got to do algebra to get X by itself. So the first thing we're going to do is we're going to get X out of the denominator. And to do that, we're going to multiply both sides by X. Okay, now after we do that, we're going to need to write this in terms of a quadratic. It's a little bit of algebra, sorry. So we would FOIL this 0.0371 minus X. So it would be 0.0371 minus X times 0.0371 minus X, which gives us 0.001376 minus 0.0742X plus X squared. All we did is square the numerator. So we're squaring the numerator and multiplying both sides by X to get X out of the denominator. And then we need to get this into the quadratic form. And to do that, we're going to have to subtract 0.021x from both sides. So now we've manipulated this equation so that it's in the quadratic form. Okay, now quick review of some algebra. When we're in the quadratic form, the coefficient in front of X squared, that's A. The coefficient in front of X is B. And the last number there is C. And what we would do then is we would plug this into our quadratic formula. So let's review what that is. Okay, so when we go to use our quadratic formula, X will equal negative B plus or minus the square root of B squared minus 4AC divided by 2A. Now, B in this particular quadratic is negative 0.0952. So that's what we would sub in for B. It's what we would sub in for B here, and we'd have to square it. A is 1. It's assumed, we don't write it. And C is 0.001376. And we'd have to do all of that under our radical and then take the square root of it. And we divide it by 2 times A, where A equals 1. So we'd plug in all of those numbers. We'd get 0.0952 plus or minus the square root of 0.0952 squared minus 4 times 1 times 0.001376. And we take that whole quantity and divide it by 2. Now we end up with 2 answers for X. And we should remember that if we were to graph the quadratic, it's going to cross the x-axis in 2 places. If we solve for it using our quadratic formula, we're going to get 2 X values. But the initial concentration of phosphorus trichloride and chlorine are 0.0371. And we're going to be subtracting X for it. But X can't be greater than the initial concentration. So this X is invalid. This can't be an option for our answer, which means X must be 0.0178. So only one of the X's is ever going to be a legitimate answer from your quadratic. So once we solve for X, we can figure out the equilibrium concentrations, which is what we're looking for. And in this case, it actually didn't ask us for all the equilibrium concentrations. It just asked us for the equilibrium concentration for the phosphorus trichloride. So to figure that out, we would take 0.0371 and subtract X. So the phosphorus trichloride would be 0.0371 minus 0.0178. So the concentration, there probably should be a molarity here. The concentration of the phosphorus trichloride at equilibrium is 0.019 moles per liter. A different variation on an equilibrium problem, but the starting point is still the same as all the other problems we did. Because we write down our reaction, we've got our ice chart, we have our K expression, and then we plug in the information we know, and then we go about our business to solve for X. Okay, a little bit harder math-wise maybe, because you have to use a quadratic, which you'll not be using very often at all in this course, but it does come up, so we did want to go through a problem like that. All right, so let's look at this question. So we have HCH3COO plus water gives us H3O plus, this is called hydronium, plus CH3COO, which is acetate. So we're taking what's called acetic acid and we're reacting it with water and we're producing hydronium and acetate. And we're going to be doing a lot of these kinds of equilibrium problems in the next couple of chapters. Now, it gives us the concentration of the acid to begin with, the CH3COOH. Doesn't matter whether this H is written here or it's written at the beginning of the formula. It doesn't matter. And it gives us Kc, and it wants us to calculate the equilibrium values. So we're going to start by writing our ice chart. So see if you can fill in the ice chart for this question. It only gives you the initial concentration of this HCH3COO. It's the same thing as this here. Okay, it tells you that's how much you have per liter. Nothing else is in the container initially. We don't know what the equilibrium values are, so they're stoichiometric based on the balanced equation. Just do the ice chart. We're going to do this one step at a time together. Now, this one's a little tricky. Remember, we talked about how liquids and solids are not part of an equilibrium expression. So we're not going to put it in the ice chart. Okay, we can't talk about liquids in terms of molarity. So initially, we've got 0.100 moles per liter of that HCH3COO, or acetic acid. And we have no, this is called hydronium, and we have no acetate. Okay, it's a pretty small K value, so not very much of this reactant is going to produce product before equilibrium is established. We don't know how much is going to react, so we're going to say X amount of it reacts. And we're going to produce X amount of our products. Now, the reason why the reaction is going to go in this direction is because we don't have any product. It can't go in this direction initially. It has to go in this direction. So negative X plus X plus X. So at equilibrium, we have 0.100 minus X, X, and X. All right, we have our ice chart. Write a K expression. Remember that if this is a heterogeneous equilibrium, liquids aren't included. Okay, write a K expression. Okay, products over reactants raised to the power of the coefficient in the balanced equation. These are all ones. All right, so what do we know? Well, we know K. So we're going to plug in 1.8 times 10 to the minus 5 for K. This is X, and this is 0.100 minus X. All right, well, if we look, that's going to end up being a quadratic again. But here's the trick I'm going to give you, and it is going to work every single time. I'm going to make the math super easy for you. If K is very small, and 10 to the minus 5 is very small, it's 0.000018. That means that not very much of this reactant actually reacts to produce product. It means that this X is essentially insignificant relative to the initial concentration. Such a small amount of this reactant actually reacts when we establish equilibrium that we can actually get rid of this X out of the equation. Okay, it's so reactant favored that we can do that. As long as X is super small, we're going to make the math significantly easier. We're going to say this X doesn't matter. And since this X with significant digits isn't going to change our answer, we can rewrite this as 1.80 times 10 to the minus 5 equals X squared over 0.100. Now it's not a quadratic anymore. Math is significantly easier. And with 2 significant digits or 3 significant digits in this problem, it's not going to make a difference in our answer. So let's make the math easier. So if we want to solve for X, we're going to have to multiply both sides by 0.100. That'll give us X squared. And then take the square root, that'll give us X. We've eliminated the need to do a quadratic. Okay, so multiply both sides by 0.100, that'll give us x squared. Take the square root of both sides, that'll give us x. So x equals 0.0013. Now think about that. This value here was 0.100. If we subtract 0.0013, it's really not going to change this number at all significantly. So we can eliminate it from our problem. That means the concentration of H3O plus hydronium and the concentration of CH3COO acetate are both 0.0013. And the acetate's 0.100 minus 0.0013, but that's so close to 0.100 that it's okay for us to do that. If we had gone through the quadratic equation, we would have gotten the same answer with a couple of significant digits. So we've just made the math easier.